Okay, good afternoon, everybody. First of all, let me, before I forget, I'd like to say thank you for Intel guys team and the team for inviting us for this summit, and also thank you to Helene and MJ for excellent work with the XL710. This is quite important piece of Silicom's portfolio. A few words about Silicom. Silicom is a hardware manufacturer, operates out of Israel. Our main business is NICs and simple NICs, and then not too simple NICs, smart NICs, NICs with switching silicons, NICs with FPGAs, and bypass NICs and switches. This is our main business. And back in Silicom, we have our lab where we examine and we do some tests with all sorts of technologies. And in this presentation, I will discuss two activities that we're doing there. One of them is trying to understand what is the best data path for OVS offload or any virtual switch offload into a hardware that includes a NIC with a switch on it. And the other part would involve a QuickAssist technology adapter that we manufacture, and the way we use it with DPDK for specific use cases. So, in the first part, I will speak about the OVS offload data path that we are trying to devise with the Intel FM10K chipset. The Intel FM10K chipset, I will speak about it later on, is as a kind of combined a switch and a NIC on one die, and it fits well with Silicom portfolio of products from back, like we've started to build similar designs with several chipsets back in, I think, 2008, and nowadays when the chipset is brought all in one, we are fully prepared to test it with some advanced scenario. I will try to walk you through the data path that we're trying to create in order to make the most of the potential offload, and on one hand, and on the other hand, trying to maintain the important feature set or important features that are part of the virtualization tools that we have. So offloading the data path onto the hardware would not hamper with other features that are important for virtualization or for cloud at large. I will try to explain why DPDK is important to us in this activity. I will try to persuade you that our activity is beneficial by showing some benchmark result that we have done, hoping to demonstrate the advantage that we see, and then we'll talk about what we're going to do next, and afterwards we will move to the next deck of slides about QuickAssist. So, yes, the FM10K is a unique device. I mentioned before that Silicom was building a NIC with a switch back starting in 2008 or 2009. We took a 1 gigabit controller, later on 10 gigabit controller, and we combined it with a switching fabric. We took a switching fabric from Fulcrum. We took the FM4K. Later on, Fulcrum became part of Intel, and we devised one single device together that acted as a NIC and as a filtering machine. And the main purpose of this device was to allow an elaborate filtering of of data. Back then, we didn't call it flows as yet. Before a traffic hits the CPU. That way, an application can try to do away with as much as non-interesting traffic that it could. So the latest and greatest FM10K made us possible. We were able to take this condensed technology that has a very large flexibility and put it in a NIC that has the same or more or less the same functionality that we're used to, but at a much higher scale. So, what makes it so unique? First of all, it's a network device. It's a NIC, so it has links, it has PHYs, but it has a very large numbers of very large number of services, not PHY services, where we could take and create 10, 25, 40, and up to 100 gigabit links. Up the data path, there is this switching fabric that consists of a large TCAM for match work and a flex pipe mechanism that is responsible for doing the actual action after the match has taken place. And this kind of device, of magical device, has also PCIe interfaces up to the host, so that if you would like to connect the switching fabric up to a host, we don't need to use an external chipset of a Mac. We have it all in. So we have by 8s. We have by 4s PCIe Gen 3, and we took it and we've created several types of devices, and we took one of those devices into our lab. This device holds 4 by 10 external links and one single 40 gig host interface, and we've tried to see how we could create a data path that would exploit the benefits of SR-IOV on the PCI front, but still would not hamper with the flexibility of the virtual switching tools. So let's go through the data path of the existing tools that we have started with. This slide shows roughly the data path of a OVS. On the left-hand side, there is a OVS like a traditional OVS, where the data path starts with a network controller underneath, and it goes up to a component in the kernel, and it moves up through a tab device through a virt.io abstraction up to the guest VM. The virt.io is the front end. Now the virt.io was the important thing to maintain, because that way we believed we could we could devise a data path that would be from one end strong, but from the other hand flexible enough to serve for purposes like live migration, for instance. The front end at the VM side is the most important thing to maintain in order to keep the possibility to use virtualization feature like, as I said, live migration or virtual machine snapshot and stuff like that. So later on, we discovered the advantage of the OVS DPDK. I will look back to the one slide backwards. The important thing that we see here is that on both cases, OVS kernel data path is a considerable, is a very important component in the data path. It consumes quite a lot of performance, and it also responsible for a considerable amount of processing of on the data path. So if we wanted to take this structure and take the data path down to some sort of a device, then then our task was to tear out some functionality from this kernel component and move it down to the hardware. And for that end, we had to have a kernel level tools and access and code. And at first, we didn't have those tools because most of the tools that are brought to configure the FM10K switching fabric are user space. And so in order to devise the data path just for POC purposes, we had to have some code development, and we wanted to avoid it. So we figured that going to OVS DPDK would be much better idea, simply because the OVS DPDK brings it all up to user space. The interface to the network device is DPDK PMD driver that acts as a data playing channel up to the OVS business logic forwarding mechanism that now is up there in the kernel, and it's easily accessible and easily easy to manipulate. And the only challenge that we had at this point is to see how can we take a hardware mechanism like the SR-IOV, like a PCIe tunneling, and connect it to this type of structure without being tempted to take to connect the SR-IOV in a pass-through mode up to a VM. That way, we are losing all the benefits of the virtual front-end device. So, yeah. So the approach that we took is we've installed the FM10K based device network interface, and we created two SR-IOV channels up to the host as host interface. And over each of them, we've operated a PMD driver, DPDK PMD driver, that acts as a data channel up to the OVS. So now we had an SR-IOV talking straight, not up to the guest VM, but to the OVS as a mediator. OVS, a business logic. Now, in this mode of operation, the virtual front end is maintained. We are not hampering with the potential possibility to perform live migration. I mean, a VM can be copied, can be taken a snapshot, and the only mechanism that the SR-IOV sees is not the driver within the VM, but it is the OVS as a data plane. And now the only element that was missing was how to associate an SR-IOV channel up to a virtual machine. And that was easily done by just adding flows that connect the PMT driver to a specific VM front end driver. Now, this has enabled us the best flexibility that we could dream of in order to install one single VM, 2 VMs, 3 VMs, 4 VMs, and create a data path, a snake-like data path across those VMs, and try to benchmark how that data is streamed and what is the effect. What is the total effect of this SR-IOV configuration? Now, SR-IOV is a PCIe tunneling mechanism. Essentially, it's supposed to enable us reach the hardware limit. I mean, if a by 8 Gen 3 PCIe bus would uphold something like close to 50 megabits per second, then probably an SR-IOV channel, not probably, well, for sure, an SR-IOV channel has its overhead, but at least we could expect that it would be very close to this number. So we have devised a flow of data, and we've benchmarked it. On each VM, we have run L2 forward, DPDK, a sample code. And we've streamed in a data from one of the Ethernet devices on the FM10K device. It was streamed up to one of the SR-IOV, let's say to the SR-IOV on the left-hand side. It was forwarded up to the VM. This VM was forwarding it downwards with L2 forward back to the OVS and down through the SR-IOV to the FM10K device, where it was forwarded to the other SR-IOV and thrown upwards to the second virtual machine, just to be forwarded outwards through the other Ethernet interface. And that way we've created the data path that we could measure. We could create this data path with a simple OVS. We could create this data path with a DPDK OVS, and we could create this data path with this FM10K with DPDK OVS, and we could measure the numbers. We could see now the differences, and the numbers are quite convincing, actually. We will go through the numbers on the benchmark results, but let me just focus for 1 second on the benefits that we've seen with the DPDK. So first of all, the user space, everything is a big plus for is a big plus for us in this instance. I mean, almost all the interesting configuration of the data plane within the FM10K, whether it would be on the switch side or on the MAC side, and for sure on the link side, most of the tools are user space. So we could do with user space very well. DPDK guys were so kind enough to implement an FM10K driver for DPDK, so it was easy to integrate, and it performed without any flaws. So so for sure it was a good idea to go for DPDK. We've maintained all the back-end and front-end network interfaces mechanism of the virtualization. I mean, we used KVM and we used virt.io front-end device, and we've used vhost user as a back-end device. We've maintained the structure, and it was a big plus for us because we could hope, as I mentioned earlier, to be able to later on support the more elaborate feature set of the virtualization tools. Now, as MJ said before in his lecture, running DPDK with some kind of a research before about where are the PCI lanes and how many cores do we have and under what power consumption policy this core operates. This is something that it is good idea to perform, and with DPDK it is also easy to take advantage of. With DPDK it is easy to decide upfront how many cores we would like to use, specifically which cores, and without the and by that we could avoid what often happens with like virtual switching per se, like standard OVS, where you couldn't know in advance where exactly the load is. I mean, the load could be on specific number of cores on socket 0 or on other cores on socket or on the other socket, and this is a poor utilization of the CPU power. With DPDK and DPDK OVS, you can better utilize the CPU power exactly with the technique and the switches and the parameters that were mentioned before by MJ. Now, the model that the DPDK enabled us to take actually full advantage of the SR-IOV without sacrificing almost anything from the standard capabilities of the virtual tools that are out there. So let's go to see some numbers, how we could see the improvement. First of all, the most simple comparison was done between standard OVS and DPDK OVS. I will not go into numbers, but we could easily see that standard OVS compared to DPDK OVS, then DPDK OVS wins by at least 4x easily. And this is with single VM performing L2 forward. The thing is that with a standard OVS, when we have increased the numbers of VM across which we've performed a snake pattern of packet forwarding, then to the third VM, we've run out of CPU cycles because it was so hard to try to optimize its operation, and we just gave up. With DPDK, we could easily scale much higher. I don't remember exactly the number, but it was much higher number of virtual machines. But then again, with SR-IOV, either SR-IOV per se standalone or SR-IOV with DPDK OVS through the mechanism that we've described earlier, we see that the improvement numbers are quite considerable. Because the only limitation that we have in this case is the PCIe bandwidth, the PCIe bus. And once we have a pathway to reach and to make the most out of it, then this is the only constraint that we have. And the only constraint that PCIe by 8 poses is close to 50 gigabit per second. So it is quite remarkable performance. I mean, inter-VM forwarding. Any questions? Excuse me? What is the? Well, I'm not a sales guy, so I cannot tell. But it depends on the specific composition of the links, whether it's a bypass device. Because if we're talking about like dual 100 gig, so probably it would cost, I don't know, don't take my word for it, but probably $800, okay? But then again, the optics would be obscenely high. But if you go for four times 10 gig with single 40 gig host interface, then the prices are different, okay? Please, yeah.
So on slide 8, I'm a little confused. So there's some interesting things. So you have the DPDK PMD, which is running in SR-IOV. Slide 8 is the one with the picture, walk through the data path. I thought it was slide, yeah, that one. Okay, I'm a little confused about what's actually going on here, because it seems like there's 2 DPDK PMD threads, but OVS is going to have a single forwarding thread as well, which is going to mean that the traffic is going to somehow go through a third core in OVS, which is actually going to do the forwarding. And I guess the performance is really good because it's simple and it fits in the exact match cache, but it seems like OVS isn't really doing anything here. Is it just there so that this is just a component so you can measure how fast things are going through it? And then what does it look like when you don't have DPDK? That's the other part too that confuses me.
Okay, that's a good question.
Good.
Well, yes. In this example, I just highlighted how we devise the data path with SR-IOV up to a VM, and you could say we've neglected, okay, the forwarding mechanism of the OVS, kind of. And this is the way we believe a proper SR-IOV advantage is achieved. Now, suppose that we have other devices within the system that we wouldn't like to have them exposed through SR-IOV up to the host and still be connected to the OVS. Then they still be connected to the same OVS, right? So there is no objection why they wouldn't be connected to the OVS. And then if we would like to have some data path from some kind of external non-SR-IOV device up to such a host, okay, we could still have specific flows tailored within the OVS data path for that end.
Okay, so the arrows here are just by way of example, because, okay, you have various flows. You have something going from host to VM to back to host and VM to VM. So there's obviously been other flows here that you use to do these measurements, I guess.
I couldn't hear this.
I'm being terribly incoherent, I guess. No, I'm just saying that the red arrows are really not meaningful here. They're just by way of example.
Yeah, right. Absolutely. Somewhere?
So all of these benefits that you have on this FM1000, is it specific to this NIC card, or is it actually some of these techniques also available on some of these other Intel NICs as well?
You're asking, let me repeat, you're asking if the FM10K is available on Intel NICs as well?
Yeah, let's say on other, let's say some of the 0182.599 or some. Is it NIC specific? Or is it, that's what I'm asking.
Well, the 599 is the 10 gigabit NIC, the best NIC I ever seen. Okay, but the FM10K chipset is a different chipset, and the Mac front is not the 599. If that's what you're asking.
Like for instance, like this way of being able to hook up your SR-IOV to the PMD and then pushing over to the user lane, the vhost, right, into the VM, right? I mean, the user lane side is pretty much very transparent to the NIC. So I'm just wondering if I have, let's say I have an existing 82599, can I still leverage the similar benefit here?
Well, okay, I understood. Well, the FM, the A2599, sorry, and probably the XL710 also both feature SR-IOV capabilities and SR-IOV, inter-SR-IOV forwarding mechanisms. So as it comes to SR-IOV only, then yeah, we're good. Probably we could do with those guys. But then again, the FM10K also has a switching fabric. So at this example, it's not pictured, but suppose we would like to have two PF, not two VFs, okay, not two physical functions connected in the same manner, and we would like to be able to forward traffic among them. Okay, so that way, this type of data path is enabled only on FM10K. Okay, the Niantic, for instance, would require an external switch for that. Okay? Go ahead.
So if I understand it right, you're sort of grazing on this but not really addressing this. One of the big applications here, Silicon does a lot of bypass adapters.
Right.
One of the applications for this is you can front end the whole sort of whatever you were going to do with a bypass adapter, DPI, something like that, with a switch, and peel off traffic characteristics that you want to handle on these VMs without destroying any of the ability to move the VMs between actual physical hardware, right? Is that overall? Okay.
Yeah.
You didn't actually say that, so it's a great architecture.
Yeah, it is.
Can you go to the benchmark slide? I want to understand the numbers a little bit. Next one? Okay. So for the SR-IOV, DPDK OVS, right, and the DPDK OVS, what do you think, why the performance is so much difference between the two? Between the first bar and the third bar?
Between the second from right and the...
yeah, the first one and the third one. What's the...
The first from the left and the third from the left. That's what is the difference between them?
Yeah, why the SR-IOV, DPDK OVS, it's so much more performant than the DPDK OVS?
Say it frankly, I'm not sure that the DPDK OVS benchmark was totally optimized. Okay, it wasn't the best optimization that we didn't consider it too much where to locate and place on what cores and so on. But then again, we got some numbers that matched the vicinity that we were aware of. Now, why it is that different? Well, I can speak for the SR-IOV. Okay, the SR-IOV is a simple case. The SR-IOV is just walking straight down to the bus, to the hardware. Why the DPDK OVS sits on this area, I am not sure I can address this question. But then again, I know that this is more or less what is acceptable in this benchmark. Yeah.
Why did you use PCI pass-through? Why did you use SR-IOV?
SR-IOV is a mechanism for PCIe tunneling, okay? But it's not necessarily PCI pass. We were not connected it in a pass-through mode straight up to a VM. We haven't done that, okay? We've done something with the some trick with the DPDK OVS. It was passed through up to the OVS, not to the VM.
So,
okay,
I have a follow-up question on that one. So,
yeah.
Why SR-IOV? What is the difference between 1 and 2 actually? Why SR-IOV directly taking it to VM is not giving a better throughput than the SR-IOV DPDK OVS?
No, it's the other way around. It's not visible, but SR-IOV standalone without DPDK is somewhat better.
Oh, okay. That is not
it's a little better, but so did that address this question?
Oh yeah. Just the SR-IOV going to the VM is that's not shown here.
It's that column, but it's hardly visible. But the SR-IOV standalone is a little better.
Oh,
okay.
I have a question. So, quick one. We have sessions and a discussion about vhost user performance.
I'm sorry, I cannot see.
I'm here. Here.
Let me ask you. Let me ask you to hold with the question until after my talk, because I have some more to cover. Please. Okay.
Sure.
Thank you. So thank you for reminding me. I'll go brief about the roadmap, and we'll go briefly to the next subject. Now that we have the data path that is actually performed, we would like to go for the missing parts, and the missing parts are mainly the control path and the actual ability to perform a live migration of VM across such installations without losing the L2, L3 states, without losing the tunneling that are configured so long as configured. And this is, in a nutshell, our roadmap for that. We'll skip this. We don't have I don't have the time for this. I'm sorry. One word about OVS. One single word about OVS. We love OVS. OVS is great. OVS with DPDK is absolutely fantastic. But then again, OVS is perhaps a little too complicated for specific use cases on places like telcos, probably, where on one hand the technology, the networking, network architecture would not use flows, would not necessarily use VXLAN. They would go for the old school. So probably a Linux bridge instead of OVS could be another appealing option for this type of data path architecture. And this is also a thing that we're going to try down the road. Okay, so I have 3 more minutes. I would like to briefly cover what we do in our lab also with DPDK and QuickAssist, and we'll be very brief about that. I will skip the introduction about QuickAssist. I'm sure most of us at least aware of the basics of QuickAssist and what are the benefits of QuickAssist. It can accelerate both compression and encryption, either symmetric encryption or asymmetric encryption and stuff like that. Okay, the use cases that we see on the field for DPDK and QuickAssist, for DPDK and crypto at large, are those. It's first and foremost IPsec. IPsec is the best use case for DPDK because IPsec deals mainly with symmetric encryption, and DPDK is optimized nowadays to support ever-growing requirements and numbers in this area. Other places that we see DPDK as an important improvement factor are in the monitoring and in the storage areas. I mean, storage people, mainly software storage people, part of their secret sauce is compression, some type of compression. And these guys, when we present them with the option for offload and increasing capabilities, increasing performance, they tend to like it very much. Having said that, most of the times, their application is standard user space application, and moving to DPDK is somewhat painful. But then again, if DPDK enables them like a quantum leap in performance, specifically with compression, then probably they would embrace it. Now, the monitoring issue is somewhat interesting. Monitoring issue is quite painful issue as it comes to encryption traffic. But in the show of hands, do you know anybody know what is the percentage of encrypted SSL traffic out there on the web compared to clear text? I mean, who thinks it's something like 20%? Who will go for 40%? Okay, yeah, it's higher. It's even higher. That's right. So, and it increases. So as it increases, it blinds those guys who try to monitor traffic, because where they are trying to monitor traffic, they from one hand cannot terminate traffic, and so they cannot decipher it. So one of our challenges in this area in our lab is to come up with yet another type of data path that would enable those guys to actually not terminate the SSL, okay, the SSL traffic, but then to monitor it through decrypting it using the private key of a server that probably can be obtained by them. The basic idea is to gather and reconstruct the TCP streams using a specific tailored TCP stack over DPDK PMD, and through OpenSSL, same way as Wireshark does. Okay, we would like to be able to offer a method to decipher and to reconstruct this session, and to see how the key exchange went, and what is the session key that was chosen, and by that to be able to let them decipher the traffic in order to be monitored without actually terminating TCP streams. Yeah. Say it again.
So there is a different solution being discussed in the IETF with SPUD and everything, where you have the firewalling devices being signaled by the end systems. And I don't know if you can always get the key if you're a device in the middle, because the whole point of sending SSL and TLS traffic is so that some man in the middle cannot decrypt it. So
No, the assumption is that I hold the private key lawfully without the need to steal it for anybody. That's the assumption. But the thing is that I want to be able to decipher without terminate the traffic. Okay. Because I cannot terminate it either because I'm not in line, okay, I'm tapped, or even if I'm in line, I still don't want to terminate the traffic. Okay? Okay, so my time is up. Thank you very much.